Welcome to Inorganic Chemistry. In this third lecture on solid state chemistry, we will discuss the thermodynamics of ionic bonding. Prior lectures we looked at the structures of simple ionic compounds and rationalized them in terms of the radius ratio rules, and also looked at defects in those structures. In this lecture we'll look at ionic bonding, and in our final lecture we'll look at semiconductors and superconductors. So before we get into the bonding, for ionic bonding, we want to look at the different types of bonding that are possible in solids, and the bonding type will determine the properties of the solids in addition to the structure of the solids. And this is adapted from Liang's tetrahedron of solids. This was actually originally described by a German chemist named Grimm, where he noticed that there are 4 different types of solids. There are metallic solids, characterized by metallic bonding, ionic solids like the binary compounds we saw in the prior lecture, and the bonding between positive and negative charges we're going to discuss today. Network covalent bonded solids like diamond lattice or polymers, and molecular covalent compounds that are stacked together in solids where individual molecules are attracted by van der Waals forces. For example, sugar molecules form crystals due to intermolecular forces holding the covalently bound sugar molecules together. So in this lecture we will focus on the ionic bonding, and ionic bonding can be described as simply a cation, positively charged cation, being attracted to a negatively charged anion. And we know from Coulomb's law that the attractive force between two oppositely charged species, the electrostatic force, is related to the charge of the particles, the charge on the positive and the charge on the negative, divided by the square of the distance, equilibrium distance, between the two particles. In this case, these particles are ions of atoms, and so the charges are related to the charge of an electron and the permittivity of a vacuum, so this is Coulomb's constant. So that's the attractive force. The energy or voltage or potential of that attraction is integrated over the distance, and so this energy is going to be negative relative to the free particles in terms of the charges divided by the distance to the first power. So this would be a simple model of attracting a positive to a negative. Now in an ionic solid you have more than one cation, more than one anion, and so how do you keep track of this? Well, here's a little picture, say, of sodium chloride, and here's a cutaway. So let's look at, let's say, center on this chloride atom here, and let's focus on the attractions and repulsions to these electrostatic forces. So we would have again from Coulomb's law, we'd have the voltage, the energy is related to the constant, Coulomb's constant, times the charge of the cation times the electron charge times the charge of the anion. This is the integral in this case plus or -1 for chloride, times the charge of an electron divided by the distance d, which is defined by the unit cell. And so here we have cation, sodium cation here. That's the positive charge, and the anion is the chloride. So that'd be -1, and that would be +1 in our case here. And they're separated by a distance d. And if we look around the chloride in the three-dimensional structure, we see that there's going to be 1, 2, 3 sodium ions, a fourth here, one up above and one back behind, because the chloride is in an octahedron, or octahedral coordinated, or coordination number 6, with respect to the sodium ions. And that's opposite charge, so that will be an attractive force. So we can pull out the constant here, and that's what we've done with this formula down here. This constant, we've put it here, and then we pull out the z. The charges are 1, and d we can describe in terms of the radius between the ions, because these are nearest neighbors. So, and there's 6 of those, so 6 divided by 1. So we have this first part here. But as we move out from the chloride, we see that there is a another ion of the opposite charge. So for example, if we start with this sodium ion here, go to the chloride as the nearest neighbor, and then if we go further out, the next nearest neighbor is another cation. So that would have a positive to a positive, a repulsive electrostatic force, and the distance between these next nearest neighbors is √2 of this distance, because this makes a right triangle, √2 of d. And there's going to be 12 of these next nearest neighbors in the entire cube. If we remember the cube structure here, we have 12 sodium ions out here around that central sodium ion. So we have, in relation to our first term, in relation to our original distance, R0, we're going to have 12 negative repulsive force at a √2 times that original distance. So we get a second term here. If we keep going out away from further and further radius away from that central ion that we're looking at the forces around, we're going to get nearest neighbor, next nearest neighbor, next nearest neighbor, √3, the body diagonal from that. So that's the eight ions in the corners, for example. And those would be chlorides, so that'd be a negative charge with the positive ions, so that'd be an attractive force, attractive energy, positive energy, and so on. We can keep going out. Now it looks like these numbers are getting, of course these numbers are getting larger, the denominator, but if we look, the numerator is not constant, not a definite trend, but there is an upward trend. So 20, we're getting out to 24 and so on. So it turns out if we just keep going out in a circle of ever increasing radius, we will get a non-converging series. To make some sense of this, we need to recognize that we can get it to convert, because again we're looking at a crystalline lattice, and so as we go out distance from our sodium ion, we're going to get layers or more unit cells, and like this sodium ion out here, only 1/8 of that sodium ion is actually in this sphere, in this volume here. So it's not a sphere, it's a cube, and the edges and corners are only partially in the volume of the cube. And so when we put these limits on here, then we will have a neutrally charged crystal and the series will converge. So we have a contingently convergent series, and the contingencies make chemical sense, physical sense, and so we end up with a value that it converges to, 1.748 in this particular case. So this value that it converges to is a constant for this type of structure, the sodium chloride structure, and that was derived by Madelung, so this is the Madelung constant. And there are a set of Madelung constants for different crystal structure types. Here's a series of the different structures that we discussed before. So we can use this Madelung constant now to calculate what is the electrostatic attraction, what is the energy, or what we're going to call the lattice enthalpy. What is the energy of attraction that's holding ions together in the lattice? And it's defined as coming from the gas phase ions. The lattice enthalpy is the negative, the change in enthalpy for this reaction, and it's going to be exothermic, but we want lattice energy as a positive value. We're going to keep it positive, so we're going to put a negative sign there. Okay, so we have the Born-Meyer equation is one way to calculate the lattice enthalpy, where we have the Avogadro's number, we have the Madelung constant from this table here. So if we know our crystal structure type, we can find the Madelung constant. We know the charges on our ions. We know the inter-ion distance or interatomic distance, which would be the sum of the ionic radii. These are all constants. And then in addition to, so this part we've seen before. This just comes from Coulomb's law here, modified by the Madelung constant here. And then there's an additional modification we need to make using the Born repulsion to take into account the fact that as atoms get closer and closer, while there's attraction between opposite charges, there's also core electrons that are going to start colliding and create repulsion. So I'm going to approximate that as 30 picometers. Okay, so we can calculate the lattice enthalpy using the Born-Meyer equation here. If we know the structure. If we do not know the structure, or the particular lattice that our compound will crystallize as, we can approximate the lattice enthalpy using the Kapuscinski equation. The Kapuscinski equation has another constant, the Kapuscinski constant, a factor gamma, again the charges of the ions, the ionic radii, and another repulsion, Born repulsion factor, slightly different than what we saw before. Where the Kapuscinski constant is 1.202 times 10 to the 5th kilojoules per picometer per mole. Again, the Z are the charges on the ions. Gamma is the number of formula units, or excuse me, number of ions, number of ions in the formula unit, and the ionic radii we're going to select for coordination number 6. So this will give us an approximation of the lattice enthalpy, assuming we don't know the structure, but we do know the formula unit. Okay, another way to get the lattice enthalpy is to calculate it using thermodynamic measurements and an application of Hess's law called the Born-Fajans-Haber cycle. And here we're going to work out an example for sodium chloride. What is the lattice enthalpy of sodium chloride? And we can get this from Hess's law. So we want to know the lattice enthalpy and that's going to be a sum of, here we have the enthalpy of formation of sodium chloride. So that's the enthalpy of formation there. Then we have, that's for the elements in their normal state, but for lattice enthalpy we need the ions in the gaseous state, so we need to get them into the gaseous state. So here we have the sodium metal, we're going to sublime into sodium gas. So that's the negative of the sublimation, heat of sublimation. And then we need the chlorine gas to be chlorine atoms, so that's the bond dissociation energy. Or the negative, actually, of half of the bond dissociation energy. And let's see. So now we have gaseous atoms. Now let's ionize them. So sodium ion, that's the first ionization energy. Or rather, this is the negative of the first ionization energy. And then here we have chlorine going to chloride, so that's electron affinity of chlorine. Oh, right, I got the electron on the wrong side here. So that is the negative of the electron affinity. Okay, so we can look up all these thermodynamic values. Heat of formation is, so that's negative 411 kilojoules. The energy of sublimation, the negative of that would be negative 107 kilojoules. The bond dissociation energy, negative 122 kilojoules. The ionization energy, negative 496 kilojoules. And electron affinity, positive 349 kilojoules. So using Hess's law, we find the difference here is 750 kilojoules. So that would be the lattice energy for sodium chloride, which you can see that's quite strong. That's stronger than a single covalent bond, for example. Okay, now some limitations of lattice enthalpy, understanding or estimating lattice enthalpy. First, the ionic radii cannot be measured directly. So ionic radii shows up here in our Bohr-Maury equation or our Kapuscinski equation. And the problem with trying to measure the ionic radius is that you can't see the ion by itself. Ions only exist in compounds, and so you have to tabulate a bunch of compound data and find an average for different coordination numbers. These thermodynamic calculations assume that the ions are acting as hard spheres of charge. We started with Coulomb's law. So that assumption breaks down when the ions are acting more covalently, as we recall from our bond type triangle. Pure ions don't really exist either, and so this assumption of pure ions is going to just be an assumption or approximation, and our values from the actual amount will be off a little bit. And then not all of the thermodynamic values are measured accurately or equally accurately. So up here, using Hess's law, we used it with the Born-Fajans-Haber cycle. We had a series of thermodynamic values that we had to measure, and we look up, and depending on how accurate those were measured, it's going to determine how accurate our resulting calculation of the lattice enthalpy is going to be. So thank you for your attention, and we will look at other types of solid bonding in the next lecture.